Hey, this is Mr. Beckstrom, and today I wanted to go over some concepts that are introduced in section 1.2 in the book, and this is listing intercepts and testing for symmetry. So I've got a sample problem right here. It's y is equal to the cube root of x, and a very important kind of thing that we need to be able to do is convert radicals into exponents. So let me go ahead and write down the formula for that. So if I have some radical with x to the raised to the a power with the b root, what I can do is I can remove the radical, take the b, bring it around, put it under the a. So this is equal to x to the a all over, and we bring that b underneath. So whatever that root is goes under there, and now you're in exponential form. So very important that we learn this. You're going to be using this a whole lot in all of the math classes, including this one from here on out. So make sure that you know this. So in our case right here, we have the cube root of x, and there's no exponent there, but remember, if there's nothing there, it's assumed there's a 1. And I'm going to go ahead and put the 1 in there just to make it a little bit easier. And what I do then is this becomes x to the hold the 3, bring it around under the 1, x to the 1/3. So these two expressions are equivalent, and we usually like to use the exponential form when we're doing math problems. It makes it easier to add exponents, do some other stuff as well. All right, so now that we know that this is really just equal to x to the 1/3, let's go ahead and we want to list the intercepts and test for symmetry. So the first thing I always like to do is just plug this in my calculator and see what it looks like. So I go to my calculator, I'm going to go to y equals, and I'm going to do x, it's this key right here, and I'm going to raise it to, and then over here I can do 1 divided by 3. So this is x to the 1/3. Hit enter. And now if I zoom, let's start with a standard zoom, and then we'll zoom out a little bit just to make sure that, that we can see this here. So it looks like it starts from the left, it kind of goes through, it looks like the origin, and then it goes to the right. So if I were to zoom out once, just to make sure it doesn't look like it goes back towards the x-axis there, let's do that. And we can see, even zooming out, it looks like it's just kind of going forever and ever, and it looks like the only intercept is actually just going to be the origin there. And we can test that mathematically as well, because if we want to find the y-intercepts, we're going to let x equals 0, and the same thing for the x-intercept. We're going to let y equals 0. So in order to find an intercept for a certain axis, you just let the other variable equal 0. So for the y-intercept, if you let x equal 0, you're going to get y is equal to 0 raised to the 1/3. And hopefully we know that 0 to any power other than 0, 0 to the 0 power, is a pretty peculiar situation and somewhat complicated, but 0 raised to any power other than 0 is simply equal to 0. So that tells me that when x is equal to 0, y is equal to 0, and that's the origin. So let's do the other one over here as well. So if I let y equal 0, I'm going to get 0 is equal to x to the 1/3. And what I'm trying to do here is I'm trying to get x by itself, and there's a couple of ways to do this. But the one thing I'd like to do is, remember, if you multiply uh, an expression by the same base, what you do is you can combine that into one expression and you just add the exponents together. So if I multiply both sides, a little bit tricky, x to the 2/3, but it'll be good. So I'm going to multiply both sides by x to the 2/3. And I don't know if you can see that too well, but 0 times anything is just 0. And x to the 1/3 times x to the 2/3, it's the same base, which is x. So we just add the two exponents together, and 1/3 plus 2/3 is 1. And so I chose 2/3 because when you add it to 1/3, you just get 1, so you're just going to get x. So when y is equal to 0, x is equal to 0, and we get that same origin point. So that would be my x-intercept, and my y-intercept would both be the origin, because that's where it crosses both the x-axis and the y-axis, even though it's only a single point. And the last thing I want to do is I want to test for symmetry. Symmetry means, is this function reflective across the x-axis, the y-axis, or the origin? Not all functions are any of those, but sometimes they are, and if we find that there's a symmetry, it really helps us when we graph them by hand. So once again, I go back to my calculator. Let's go back to Zoom Standard, just to get it back in there. And if this was reflective across the y-axis, then it would look like this. It would be like the y-axis was a mirror. So it's definitely not, because your line would be up here, or it would be all the way down here. It'd be like this y-axis is a mirror. So we know it's not reflective across the y-axis. Same thing with the x-axis. If it was reflective across the x-axis, if you had this part of the graph here, it would come right back up there and just mirror it across the x-axis. And then the origin is any point on one side. You can draw a line right through the origin, and the same distance away you get a point over there, which it does look like it's going to be reflective across the origin. And in order to test those, in order to test whether it is reflective across the y-axis, we can take the original function and replace x with negative x and see if we get the same function back. The same thing with, and I'll just do one of these. So let's test to see if this thing is reflective across the y-axis. So in order to do that, what I'm going to do is I'm going to write the function down again. So y is equal to x to the 1/3. And in order to check to see if this is reflective across the y-axis, I'm going to replace x with negative x. Negative x to the 1/3. Same thing. And if I do that, this is a cube root, which is an odd root, which means that it's going to stay negative. So this is equal to negative x to the 1/3. If it was even, it would be positive, but it's odd. And this is not the same as this. So that tells me that this is not reflective across the y-axis. And finally, to check to see if it's reflective across the origin, I replace both of them with both the y with negative y and the x with negative x. So I go back here, I say we're going to replace y with negative y is equal to replace x with negative x to the 1/3. This is going to give us, this is just negative y is equal to, and we solve from up here, when we have an odd root like this, the 3, that's going to give us a negative x to the 1/3. And then if I just multiply both sides by negative 1, I'm going to get the original function back. Y is equal to x to the 1/3. And because I got the original function back after replacing both the x and the y with the negatives of those corresponding values, I can see that this function is reflective across the origin, and like I said, that the kind of the distance line through the origin makes sense. And also it means that for every value x, y, there's also a negative x, negative y there. So if there's a value of 1, 2, then that means there's also going to be a negative 1, negative 2 on that graph. All right, well, that's it for today. And if you have any questions, please make sure to let me know. And I hope you have a great rest of your week.